So absolute convergence is a little bit easier to test for than regular convergence. The trade-off is then we lose out on those series which are not absolutely convergent, but still converge as long as they have their minus signs, the conditionally convergent series. Now, we have some tests to figure out whether a series is absolutely convergent. One of these is called the ratio test. So instead of comparing the series to another series, or comparing the series to an integral, we're going to compare the series to itself. So we're going to look at the ratio of consecutive terms in this series. So the number I'm currently at is a sub n. That will be my denominator. The next number on my list is a sub n plus 1. That will be my numerator. We're going to throw absolute values on that and take a limit. So if that limit of the ratio of consecutive terms converges to some real number, then we can say whether or not the series is absolutely convergent. So if that limit is a number less than 1, right, since I'm using absolute value bars here, I can't get negative numbers. If that limit is less than 1, then the original series is absolutely convergent. And this is basically saying that the series itself is like a geometric series. Because if I did have a geometric series here, then no matter what n would be, my numerator would be a to the power r to the n. Denominator would be a to the times r to the power n minus 1. So that limit would just be my ratio, r. r less than 1, the geometric series converges. R greater than 1, then the series diverges. So in the ratio test, the limit of the ratio of consecutive terms in the series in absolute value is positive, or if it go even worse, if it goes to infinity, then the series is divergent. So this can tell us if a series is absolutely convergent, or it can tell us if a series is divergent. If the limit of this ratio of consecutive terms is equal to 1, though, the ratio test is inconclusive. Not enough information. We cannot say whether or not the original series converges, and we'll need to use a different test. So as an example of that, let's look at the series 1 on n squared, which we already know converges. If I try the ratio test here, my ratio of consecutive terms after I do my division of fractions looks like n squared on n plus 1 squared. And that just goes to 1 as n goes to infinity. So the ratio test has nothing to say about the convergence of this series, even though we already know that series converges. So this test does not handle all kinds of convergence.